So what did I miss? What did I miss?
Welcome to the What Did You Miss video for Thursday, October 15th and Friday, October 16th. We used some Nearpod slides in class today to practice drawing force diagrams and applying Newton's first and second laws to predict or analyze the motion of objects. After we worked on those problems for the first half of class, we then proceeded to work in groups in breakout rooms on a variety of activities related to forces, including a PhET simulation. Now, the first question that we came across was to draw and label all of the forces acting on an object pushed horizontally at a constant velocity across a rough floor. And so I gave you guys this background image, and then you would click on it to be able to draw on the image itself. And to do that, you would go to the So What Did I Miss page in our classroom page. So I'm going to show you where to go so that you can fill these out if you are not in class to do so on Thursday or Friday. So all I did was log into our classroom page and go to modules. And under the module, you'll see where it says Notes and Learning Resources from Thursday, October 15th and Friday, October 16th. And that is where we're going to click to have access to the slides that I'm currently showing you. And these are self-paced, so you can click through and you would then be able to edit, and it would record your participation. So again, if you were absent from class, make sure to fill out this first slide to hit the Join Lesson button so that way it records your responses and you would get credit for completing this after the fact if you were not present in class. If you want to try it again and see how you do, that is also an option. So again, these are here for you to practice with the questions at hand. So that is where you would find the Nearpod. Now, if we're breaking down this question, there are a few things that are in the prompt that give us clues as to what to draw. All right, so let's go through and just annotate our question. So we know that the object is moving horizontally and it's being pushed, which tells us that there is an applied force happening in the x direction. So we should absolutely have an applied force. So let me do that one more time. All right, so we have an applied force, and it's moving at a constant velocity, which means that there is no acceleration. And that also means that the forces are balanced, meaning that when we draw our diagram, that our horizontal forces should be equal in size, opposite in direction, because there is no net force, because our acceleration is 0. And then last but not least, there is a rough floor happening, so we know that there will be a friction force opposing the motion. So just from the prompt itself, we know for sure that there has to be an applied force and a friction force. Now we can make an assumption that the box or the object is on Earth. And one other thing that we can show from the question is that it is on a floor. And because it is on a floor, we know that there have to be two vertical forces because this is moving horizontally. And we know that those two forces would be gravity downward because it is on planet Earth, and the floor will supply a normal force. So our final diagram should incorporate all four of these forces. So gravity, normal, friction, and applied. And because this box is not accelerating upward, then we know that the normal force and gravity have to be balanced. It's not accelerating up or falling through the floor. And because friction and applied force are balanced, we are moving at our constant velocity. So that would be how we would draw this free body diagram with those forces involved. We then looked at a problem where we would find the net force on the box. Remember, the net force we find by adding all of the vertical forces to find a net vertical force, or in this case, all of the horizontal forces. Now, in physics class, remember that right is typically a positive direction, and left we use a negative sign to indicate the direction. So if we were to add our forces, so our net force equals the sum of our forces in a particular direction. So if we're looking horizontally, we have 3 forces acting on this box. And if we were to type those out, using the rules that we just laid out, we have positive 10 newtons to the right, plus, because we're summing, we're adding our forces, negative 5 newtons because it's pointing to the left, plus negative 12 newtons because it's pointing to the left. And when we add those all up, 10 minus 5 minus negative 12 gives me a value of negative 7 newtons, which means that our force, our net force, is negative 7 or 7 newtons to the left. Now, another way you could approach this problem is by finding the net force acting on each side and then comparing them. So like, for example, on the left-hand side of my box, I have 17 newtons of force. On the right-hand side, I have 10 newtons of force. And if I look at those, 17, I can tell right away, is larger than 10. And what that tells me, because 17 is larger than 10, is that the direction of the bigger force to the left is the direction my box is going to go. And that is why my net force will end up being to the left. So you can approach this either way. You can look at the math, or you can find the total amount first on each side and then compare or subtract that. There are 7 more newtons going to the left, so that's why the net force is 7 to the left. Our next question in Nearpod is using Newton's second law, which is F net equals m times a, the mass times acceleration, to determine what the acceleration of the box is, the same box we just looked at. So we just determined that the net force on this box is 7 newtons to the left. That means we're going to use that information paired with the mass of the box to determine the acceleration. So we know our net force is 7 newtons to the left. We know our mass is 5 kilograms. And so the only thing we don't know is acceleration. And we're going to use this second law equation to find it. So you should do some algebra. And in the end, you should end up with 1.4 meters per second squared to the left as your acceleration. So make sure to check your work, and you would show your work before submitting through the Nearpod. Now, after that, I did demonstrate how to use the activity, the PhET simulation, to take some data for our lab activity. And so if I scroll down here on the So What Did I Miss page, this is actually a video on how to take data in the experiment. So that would be a useful tool to look at for sure. Just a real quick reminder that in part 1, you are changing the mass of the object. So like you're keeping the force the same at 100 newtons. Hold on. Let me freeze everything. So we're keeping our force consistent at 100 newtons. Hold on. We'll get it to exactly 100. So we're keeping our force constant at 100 newtons. We are timing how long it takes for the box to accelerate to a velocity of 40 meters per second. So my timer would be running. And as that's occurring, you would get some data. And ultimately, you're going to create a graph for me. Now, the graph you are making for part 1, where you're changing the mass and keeping the force the same. Oh, I do not want a circle. Hold on. So the first graph you're making is going to be of the acceleration on the y-axis and the mass, the total mass that you're putting on here, on the x-axis. So that is going to be graph number 1. You're literally going to Google physics aviary graphing tool. And this quick graphing program is the one you want to use, where you can then type in what's on your x-axis, what's on your y-axis, and plug in your 4 data points. The reason why I recommend this is because of the curve fit button. The relationship you're going to see between mass and acceleration should not be linear. And so when you see the shape that best matches your data, you're going to be able to pick that from the images here. In Desmos, you don't have best fit lines to choose from. You would have to know the equation of the line, and that is a little bit more complicated. So that's why I recommend using this tool to create your graphs. Part 1, you are graphing your acceleration versus your mass. In part 2 of the activity, you are going to keep the mass the same for all your trials, and you are going to be changing up the force each time. And remember to set friction to 0. And so for your second graph, you are going to create, instead of it being acceleration versus mass, this time it will be acceleration versus the force in newtons. So your first graph will be acceleration versus mass for part 1, when we're changing up the masses. In the second portion of the activity, when you change up the force, you are going to graph acceleration versus the force on the box. All right, so those are the 2 graphs you are making, and then you'll answer some questions about it. And that is the demonstration given in class today. So at this point in class, everyone was given the opportunity to spend about 20 to 25 minutes working on an item of your choosing. So if you were all caught up and ready to start the PhET activity that we just demoed, then you were able to do so. If you needed to catch up on the Newton's second law notes and Edpuzzle and practice problems, that was also an option. And you also had the option to work on your force diagrams worksheet. So everyone had something to work on. If you had finished option 2 or 3, you could switch to a new task during class, and it was a way to work in breakout rooms with other people working on the same things as you. And then the to-do list before our next live class was to work on your forces PhET activity and to work on later missing work. So if you have work from weeks 5 through 7, these are some of the assignments that have been collected in that window, and that work will be accepted through November 1st. After November 1st, that work will not be accepted. So if you owe me missing work from any of these assignments from those 2 weeks, please either ask questions during my live office hours this week or Wednesday check-ins, and I'll see you at our next class.